So relative motion looks at objects that are in motion and what it's in relation to. So like a plane in relation to the wind blowing, or a person sitting in a boat contrary to the current of the river. Okay, so it's in relation to something else. So when we look at relative motion, we have to look at multiple different kinds of measurements. We're going to look still time, still velocity, still distance, but we need to make sure we understand which piece of information belongs to which character in the story. Like, does the information go with the boat, or does the information go with the shore, or does the information go with the current? Okay, so we're going to use trig again, and we need to make sure we're all in the same unit, nothing else has changed. Okay, and then times on all sides of our triangle is the same, because we're breaking it down into step-by-step problems, but time can't change. 5 seconds in the river or 5 seconds in the boat, it's still 5 seconds. Okay? All right, we're just going to start with problems. It's just easier to jump right in with both feet. I just can't really see that, can I? There we go. So a boat with a speed in still water of 5 meters per second is heading west across the river. The river current is 2.5 meters south. What is the velocity of the boat relative to the shore? So in order to be successful at these questions, you have to draw the picture. Don't try and bucket, just go with it. Draw the picture. So here's the shore. Okay, and so then we look at it and it says that a boat with a speed of in still water of 5 meters per second is heading west across the river. So here's our little boat and it's going this way. Okay, that's our little boat. Now it says the river current is 2.5 meters south. So the current of the river is going this way. So this is 5.0 meters per second, and this is 2.5 meters per second. One belongs to the boat, one belongs to the river. The question is asking us relative to the shore. So I'm going to complete my triangle. Okay. And this is the part that becomes critical. The angle needs to be relative to the shore. That's this angle. Okay. When we draw a rectangle and we split it like this, what do we know about this side and this side? They're equal. What do we know about this side and this side? They're equal. Okay? Just keep those pieces in your brain. All right, so it's asking us what is the velocity. So we need this velocity here of the hypotenuse, because that's, when we think about it, if we were to put a boat into the water and we just let the water move it, there's no motion, even though the boat is pointed this way, if the current is running this way, it's going to eventually push that boat that way, right? It's just going to have drift. Same thing, don't do this at home, but if you're driving your car and you take your hands off the steering wheel, if you happen to be on a little bit of a bend, your car is going to follow that bend as opposed to go straight down the road, right? If there's a hump in the road or grooves in the road, your car will go that way as opposed to going straight where you want it to go. I test drove a car that has lane assist, and as long as it can see the middle road, the center line, and the shoulder line, it actually, like, and I like took my hands off the wheel, and it turned. We went on a speed corner, and the car drove itself. And then it goes ding, 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 and there's like hands on the steering wheel flashing in red. Like, put your hands on the steering wheel. It was really cool. I'm this close to buying it, but yeah, it was really cool. So how do we solve for v? Yeah, we're simply going to look at a squared plus b squared is going to be equal to c squared, and we're solving for c. So it's going to be the square root, and I'm going to put in brackets here that c is actually our velocity. And so we're going to go a squared, it doesn't matter, 5 squared plus 2.5 squared. And then we're going to take the square root of that, and we're going to get our velocity. And so what do we get for a value? I'm going to ask Avery to calculate it and Rayleigh to fact check it. Perfect. 5.590, let's say 2. Yeah, it's 169944. And then our units are meters per second. Okay, velocity is scalar or vector? Vector. So that means it needs a direction. How do we figure out direction? If I want this angle here, how do I figure out this? How do I figure that out? Well, I need to kind of like step back a little bit, and I can look at that. I know this. I know this here is 5.0, and I know that this here is 2.5, because we all agreed that the two long sides are equal and the two side lines are equal. So now it's not quite so intimidating when I don't see any of those numbers. How do I solve for this angle knowing that I have these two side lengths? We're going to use the inverse tan. Yep. So theta is going to be equal to inverse tan. And tan is what? Opposite over adjacent. So what is opposite of this angle? Which? 5.0. And what's adjacent to this angle? 2.5. So then I get what? Rebecca is going to calculate it, and Paulina is going to fact check it. And then what's the rule of thumb with degrees? Regardless to sig digs in the question. Maximum 1 decimal. Okay, so now let's go back to the question. How many sig digs are in the problem, Cameron? 2. 5.0 and 2.5. So that's 1, 2. 9 will play a factor on the 5. So we've got 5.6 meters per second, 63.4 degrees, And we don't need to know if it's north, south, east, or west. We just need to say this. Relative to the shore, because that's what the question asked us. Okay? Questions, comments, concerns? Thumbs up, thumbs sideways, thumbs down, thumbs sideways. Okay? Let's do another one. Well, let's continue on with this one. Okay, so we're still the boat in the water. And now it's asking us if the river is 2,395 meters wide, how long does it take the boat to cross the river? Okay, so here's our original diagram, like this, right? The boat was going west, the current's going south. This was 5.0 meters per second. This was 2.5 meters per second. We ended up doing this tip to tail. Okay, we know that if I take in and I draw the other diagram, okay, we know that the river is 2,395 meters wide. So it's asking us, we know that this one was 5.6 meters per second. It's asking us to figure out the velocity. What do we know, or asking us to figure out the time, sorry. What do we know about velocity, time, and distance in the horizontal direction? What is the only formula that works in the horizontal direction? Velocity equals distance over time. Okay, because we're in the horizontal. So what is the information that we know for horizontal? Well, in the horizontal, we have 5.0 meters per second, and we have 2,395 meters. That's what we have in the horizontal direction. So distance, how do I rearrange the formula? Joyce, what do I get to solve for distance? Oh, we should be solving for time. Okay. How do we solve for time? How do we rearrange the formula for time? Distance over velocity. How do we move time? First, we multiply it out because we need to take it out of the denominator. So then I have velocity time is equal to distance. And then I want to isolate time, so I have to divide out velocity. So it's distance divided by velocity is equal to time. Okay, so I'm going to plug those numbers into my calculator. Cameron's going to calculate it, and Joyce is going to fact check it. How much? 479 what? Seconds, right? Because we have meters divided by seconds, so we're left with seconds. And we have to go all the way back to the original question because the limiting value in there is 5.0 meters per second. And so how would we report this answer if we could only have two significant digits? Because 48 is not the same thing as 479. What do we do? Princess, how would we write our answer? Right? Because here's our decimal and we would move it 1, 2, and then 9 would have an influence on the 7. It would round it up. So 4.8 times 10 to the power of 2 seconds. Questions, comments, and concerns? Because this is the only formula that works in the horizontal, right? The width of the river, which is a horizontal direction, is 2395. So we can only take the equal velocity in that direction. Only the components that are in the horizontal can we use. Any other questions, comments, or concerns? We're good to move on. We're still at a minimum of a thumb sideways. Any thumbs down? No? All right. How far downstream is the boat when it reaches the other side of the river? So we went across the river this way, 2,395 meters at 5.0 meters per second. The river is moving this way at 2.5 meters per second. We ended up doing this is what our actual drive looked like. And we know that in this section, time is equal to 479 seconds. Okay? What we need now to do is look at numbers in the vertical. Okay, so we know that time in the horizontal is equal to time in the vertical. And because all we're doing is we're looking at this, we're going to bend the rule of the only formula that works in the horizontal right now can also work in the vertical. Because we're only looking at this particular information. Okay? So we have in the vertical, we have 479 seconds. And we have and we're looking for distance. Because we're only looking at those three particular things, and we're not like launching upward into the air, we're not throwing it straight across, we're not dropping it down, we're just a boat in a river going with the current, we're not concerned with acceleration. So we're going to use this formula. So I know that the rule is velocity equals distance over time is only used in the horizontal direction, and we're looking at a quote unquote vertical direction. However, we're on the same plane as the horizontal. It's not like we're doing this. We're on the same plane. We're moving this way. Okay? We're bending the rule. So distance is going to be equal to velocity times time. velocity is 2.5 meters per second. Time is 479 seconds. I am going to get Princess to calculate it and Aiden to fact check it. Okay, now, what is our actual answer going to be? How many significant digits? How are we going to write it out? Daniel, how many significant digits are we looking at? 2. Is 12 the same thing as 1197? No, so how are we going to write our answer? 10 to the power of 3 meters. And the reason that this has no direction, that we don't say south, is because it's just asking us how far. It just simply needs a distance. It doesn't need a displacement. So once we do that, what we're going to do, and I'm just going to move this picture over here, not changing anything. We have to send our boat upriver. The current of the river is this way, and this is my projected path. This is my resultant vector. We know that the boat traveling in still water travels at 5.0 meters per second. And we know that the river current going south is 2.5 meters per second. And so what we're looking for is we're actually looking for that angle. What angle relative to west do I have to send my boat? So when I look at this angle and I have these pieces, I'll switch back to black. When I have these, when I have those 3 trig options, here's my angle. What is 2.5? Opposite, what is 5? Hypotenuse. Which math function are we going to use? Opposite and hypotenuse. Which one are we going to use? So we're going to use sine. Okay? Sine is equal to opposite over hypotenuse. So if I want to find the angle, I'm going to use the inverse sine function. So we've been doing this all along. We've just been using tan. Now we're going to use sine. Opposite is 2.5 meters per second. Hypotenuse is 5.0 meters per second. So what does my theta end up being? What value do we get for theta? And make sure your calculator is in radians if you haven't already done that. Or degrees, sorry. And check, because for whatever reason, Avery's kept flipping back to radians, even after she would set it to degrees. So always when you're doing a calculation, just take a quick look. Make sure your calculator, all of physics, we don't work in radians. I can't even begin to describe it to you. You guys have more knowledge of that than I do right now. I'd have to sit down with the textbook and relearn it. We only use degrees. Okay? What do we get for a value? 30 degrees. 30 degrees tells us nothing. We need a direction. So when I look at this angle, my main axis is west. And in order to get to this hypotenuse line, I go in which direction? North. You're close. I have to go north of west. West of north, Rayleigh would be this angle here. And it would be 60 degrees. If you did that part, you'd have gotten the answer. If you said 60 degrees west of north, you'd have gotten the answer right. Okay? And so it says, what direction does the boat need to head so that when it reaches the opposite shore, it is directly west from the starting point? When we go back to the original question, it says, what is the velocity of the boat relative to the shore? So, is this angle here relative to the shore? What's it relative to? It's relative to the river. This angle here is relative to the shore. Or, even better, is because this goes all the way back to the original question, and it better answers this particular question. What direction does the boat need to head so that when it reaches the opposite shore, it is directly west from the starting point? Well, if I said go 30 degrees north of west, that means that you've got no point of reference. If you were a seafarer, you would have no point of reference. But if I said go 60 degrees relative to the shore, you would know to go out that way. Okay? This part gets a little bit confused. I wouldn't mark you wrong. If you did this and you stopped your question at 30 degrees north of west, I wouldn't mark you wrong. You would get full credit for that answer. This 60 degrees relative to the shore happens to be the better answer. Okay? So if this works in your brain and this muddles your brain, start with this. Okay?